Hey, what's up YouTube? In today's video I'm going to talk about interactive foliage and explain how I built this cool effect. Now I'll keep it somewhat high level and explain the theory, but I won't take a deep dive into the code. This video is not a tutorial, it's a bit of a devlog as well as a technical breakdown, lots of rambling, so feel free to use the timestamp below to skip some chapters. Now, interactive foliage has been a dream goal of mine for a very long time now, and is probably the reason why I switched from environment art to tech art, if I'm being honest. It's a rabbit hole I've yet to dig myself out of. I've toyed with lots of solutions, and some were very bizarre. Let's take a brief look. The most straightforward solution to implement some kind of interaction is, of course, via Vertex Shader. Forward your character's world position to the shader and offset vertices away from that position, and that's it. It's super simple, but not that great looking, obviously. You can of course improve that with Pivot Painter and similar techniques, but the main limiting factor here is that there's no persistent state. There's only the data at a given frame, so it's pretty much impossible to create an effect that evolves over time, if that makes sense. Foliage that behaves like physical things, that wobbles and settles over time, right? So then I tried a mostly shader-based solution still, but with a tiny bit of blueprint logic layered on top, to give extra information to the shader and create a more intricate effect. Better, but still not that great. So next I tried a render target based solution, and that already started to be quite a decent system. You can store a lot of information in render targets and have that information persist over time, and so that lets you create some sort of simulation, I might say. Something that uses the previous and current state to figure out what's next. It's one of the most common methods and is still widely used in the video game industry. It has limitations though, of course. This is a render target, so it's 2D, so most often this is used to draw effects at some world position in X and Y. It's a top-down projection essentially, meaning it'd be hard to interact with the branches or leaves of a tree without affecting the grass underneath it, or the other way around. Now you could create multiple 2D render targets to support different layers or altitudes, I might say, or you could even switch to a volume render target and do things in 3D space. But even then there are other limitations. What if two foliage instances are close to each other in world space, yet have different physical properties? Let's say one is way more sturdy than the other, and thus should settle way more rapidly and maybe not bounce or bend as much or something. That's really difficult to do with render target based solutions where you typically encode the state of one single shared simulation at discrete positions in the world, if that makes sense. For that reason, it's quite hard to create very precise interactions, like push a specific branch of a specific instance and whatnot. Anyway, that's what I may call a world-based solution. You store the state of some kind of simulation at different positions in world space. So another solution would be instance-based, where you store the state of the simulation per instance. And that can be done in many ways. I tried swapping in and out foliage instances with skeletal meshes that could then be individually deformed with physics. That was a long time ago, time flies. I actually just recreated this a couple of days ago, just to have a clip to show in this video, and I shared that clip on Twitter, and it received a lot more attention than I anticipated, so I'll definitely make a breakdown video very soon and release the project on my Patreon as well. Now that's a great solution, and probably the best bang for your buck when you think about it. It's relatively easy to set up, at least in UE, and the result can be really good. But it's not really scalable though. It can be very costly if you don't know what you're doing or when used at a large scale. So you're most likely to see this kind of implementation in slow-paced stealth game where you can quite easily control the amount of instances you're interacting with at a given time. Skeletal meshes are really slow to render compared to static mesh instances. The physics simulation is done on the CPU, and using lots of constraints and lots of rigid bodies can definitely hurt performance. But it's definitely shippable if you're cautious. Next I tried swapping in and out foliage instances with a pool of static meshes with pre-allocated dynamic material instances, so I could send per instance data using a bizarre custom simulation system. I did that before per instance custom data was a thing in UE a long time ago, so more recently I tried a more robust solution with, well, per instance custom data. Now, a per instance solution is great, but it comes with limitations as well. Nothing's perfect. Most solutions, like mine, only simulate nearby instances for performance reasons, and so applying wind is not really possible. You'd have to apply wind, well, everywhere, and thus simulate every single instance. A bit tricky, right? Now, you could of course still apply wind animation using a Vertex Shader, but that would create a discrepancy between the visual and simulated state, if that makes sense. The wind wouldn't be included in the simulation, is what I'm trying to say. For instance, with the skeletal mesh method, rigid bodies are attached to bones, right? So applying some kind of wind animation on the vertices would certainly animate the mesh, but the physical simulation would still occur as if the mesh was not animated, based on the rigid bodies. It might not be that big of a deal, but my point is that an instance-based simulation is likely to conflict a bit with wind animation, because it is most likely not part of it. That's why I tend to differentiate foliage that is dynamic, that reacts to the wind and all, and foliage that is interactive, that can be pushed around by your character, nearby enemies and whatnot. Most often you have two separate systems to support both dynamism and interactivity, because each feature comes with its own set of constraints and challenges. Speaking of wind, I recently made a video showcasing a very cool interactive 2D wind system of mine, go check it out. But yeah, the sky's the limit. At one point I even toyed with GPU instancing using Niagara, so I could then send each instance data from simulated particles. I just love that kind of stuff, but I'm still very far from a top-of-the-line AAA solution though, something ideally almost entirely GPU based with compute shaders and whatnot. Similar in a way to what's done in Alan Wake 2. When you think about it, this kind of system behaves a bit like a particle system. Each particle knows the particle it's parented to, so you can create a hierarchy, and so I usually call this a strand-based simulation. Each particle can then react to nearby characters, to some effects, and to the wind to create a feature-complete simulation. You then quote-unquote export the strand's position and rotations into a render target. Next, you give each foliage instance a way to know where its root strand is in the render target. And then, using vertex color or UVs or any other means, you encode the strand index per vertex to sample the correct strand transform for that vertex and thus deform the mesh via Vertex Shader. That's a bit simplified, but that's pretty much it. That's my dream goal, and today I took one more step towards that goal and I'm very pleased with the result. Please be aware that this is, however, a proof of concept. It's not usable as is because it's a blueprint solution, so not performant at all, and it just works on one single instance. But I wanted to figure out the key principles first, how the simulation works, what data I need, and so on. And that's obviously much more easily done at a small scale in blueprints or even in C++ than with tons of instances on a compute shader, especially in UE. UE's rendering pipeline is quite scary and I've yet to seriously dive into it. Building custom compute shaders and whatnot seems a bit involved, so that will be for a later date. For now, this is all I got, and I'm quite happy with that already. Baby steps, you know. So what exactly are you looking at? Well, let's take a look, shall we? Alright, where to begin? I guess the first order of business is to construct the strand hierarchy, and at first I used a skeletal mesh to do this. I created a simple armature in Blender that I imported into UE using FBX. Then in UE I looped through the bones to fill an array of struct to create a list of particles. That approach, however, proved to be troublesome because bones can be a bit annoying to work with. Let me explain. Bones can be thought of as strands in your DCC software. They have a start and an endpoint, and thus a length, role, and information about the way they are connected to their parent. But once imported into a game engine, things become quite different. To summarize, a bone merely becomes a transform in parent space, plus a way to point to that parent. That's it. And that's plenty enough and very efficient to drive skeletal animations. But to create my own custom strand hierarchy, that proved to be quite limiting. First, in engine, bones have no information about their initial length, and I really need that information. You'll understand why later on. That's no biggie though, just have to get the parent bone's location and do a distance check and that's it. But note that I'm going backward, I walk up the hierarchy to create strands. So each bone is a strand's endpoint. That means the root bone results in a strand that has no length, because it has no parent. So that strand is just a point, and that kinda breaks my paradigm. Moreover, I no longer can create strands at the end of each bone chain. For instance, getting that bone's location would give me this point, and so to create a strand there, well, I would need an extra bone. And that's precisely why FBX exporters typically have an option to add an extra bone at the end of each bone chain, to be able to get the last bone length if needed. But still, that option doesn't solve everything. Because I'm walking up the bone chain to create strands, I end up with duplicate points where there are splits. For instance, that bone here has this location in engine, and so I get the parent bone's location to create this strand. But that other bone also creates a point here, resulting in a duplicate strand, and that obviously proved to be an issue during the simulation. Each point would be individually simulated, resulting in two strands pointing to the same branch but having different transforms, if that makes sense. Now I could add constraints on these points to ensure that they stick together, but that's extra steps in the simulation I'd gladly skip. I could also scan the bone hierarchy and figure out where duplicates are by looking for bones that have similar parents. But that's a bit annoying to do, and it doesn't even solve all my problems anyway. Here's another issue. I can get a bone's location and its parent's location to create a strand, cool, but I don't know how that bone is quote-unquote attached to its parent. It could be well attached, or it could be arbitrarily offset from its parent. Thus, this bone here, because parented to that bone, but offset from it, creates this strand. And that, again, created an issue during the simulation. Now, I could very well simulate strands just like skeletal meshes are animated, meaning I could propagate each bone's transform in parent space along the bone chain, but I guess that wouldn't be the most efficient solution. I'm really looking to create the most simple position-based dynamic simulation, something a GPU could process in no time. If I'm looking to simulate a very large amount of strands, efficiency is of utmost importance here. And walking up or down the hierarchy several times and looking up data stored in different places in memory for each parent doesn't sound like a great idea. So, a bit of a puzzle. And maybe I'm missing something here, I don't know, keep in mind I'm new to this. However, I'm pretty sure that this traditional bone method is what's used in Alan Wake 2. You can clearly see the extra bones that connect the branch's root bones to a certain trunk bone, right? That's the same kind of hierarchy you get to see in UI with a regular skeletal mesh, because that's just the way bones and skeletal animations work. This armature in your DCC software sort of becomes this in engine. So yeah, I'm not sure how the strand simulation is performed in Alan Wake 2, but it seems at least that they stuck with a skeletal hierarchy. And I personally encountered lots of difficulties with this approach, so I chose to do things differently. First, I only care about bone tips now. That lets me get rid of the duplicated points problem and the extra bone requirement to create the last strands. Second, I assume the root is always at 0, 0, 0 in local space. So the first point has no parent, thus I know it's the root strand's tip, and so I know that strand goes from 0 to that point. Third, I assume no bones can be offset from their parents. Well, they can, but only along the parent bone's main axis. That should, however, be enough to build any kind of foliage structure. Trees, bushes, twigs, whatever. When you think about it, things are connected and attached to each other in real life, so there's no reason for a strand to not be physically connected to its parent strand. Having made this assumption, I then only need to know the normalized distance to the parent strand start point to figure out this strand start point using a simple linear interpolation. Which brings me to the next chapter. If a skeletal mesh and an FBX file would do me no good, well, I'd have to create my own custom file format. Oof, sounds fancy, and sounds difficult most of all. Well, no, not really. Unreal Engine can import CSV files, spreadsheets. So why not write the data of each strand in a spreadsheet and import it into UI? That's what I did. Using a simple Python script in Blender, I create a CSV file and write the header. Next, I loop through the armature's bones and compile the necessary data. Bone tip's position, length, parent bone name, and normalized distance along the parent bone's main axis. Append that to the CSV file and voila, custom file format. Now it's important to leave that first cell blank, because that CSV file is going to be converted into a data table once imported into Unreal Engine. And a data table is basically a map, a dictionary, meaning it's a struct associated with a unique name. So that first column is a data table row's name, and the other columns are part of that struct, if that makes sense. So I built a blueprint struct to match the CSV columns. Same variable names, same order, okay? Next, just have to import that CSV file, specify the blueprint struct I just created, and tada, here's the data table. Then it's just a matter of listing all rows in a blueprint, loop through each row to get that row struct, and done. Now, what to do with this struct? Well, it's almost like I need 3 different structures in total. One struct for the data used to import the asset and create the hierarchy, that's the CSV file, one struct to contain the simulation data, and one last struct, although it's technically not a struct, for the data to send to the shader to apply the deformation using a Vertex Shader, right? So let's focus on the simulation for now. What data do I need for the simulation? Well, I'm going to simulate a bunch of particles, so I definitely need a position. And I also need to store the previous position. The physics simulation I'll explain in a second is heavily inspired by position-based dynamics, so it's all about positions, okay? The delta between the current and previous positions give me the velocity, and that's all I need to know to apply movement, forces and whatnot. Speaking of forces, if I'm going to add some kind of force or constraint so the overall structure tries to retain its initial shape, I probably need to store that point's initial position as well. However, I'm not going to do that. I'm instead going to store the strand's initial direction and length. Turns out that's all I need. I'm also trying to think ahead and see how I could shave off bits from this structure. For instance, these vectors could probably use 16 bits floats instead of 32, if the simulation is done in local space, relative to the instance, right? You don't need as much precision in that case. And same for the strand's length. That direction, that unit vector, could probably also be packed into a single 32 bits float using bit packing once the simulation is ported to the GPU. If I'm going to store 500,000 or even 1,000,000 of these points to simulate tons of strands on the GPU, it's important to store as few bits as possible per point to keep the simulation buffer as small as possible. It's not necessarily about memory usage, more about memory bandwidth. Also, 16 bits arithmetic is much faster than 32 bits. Anyway, there's not much I can do in blueprints regarding bit usage, but I don't care at this point. Again, it's just a proof of concept. Next, I'm also going to store the parent index and the normalized distance to that parent along the parent axis, like I explained earlier. Finally, I could store extra information for the physics simulation, maybe have a drag, stiffness and weight parameters per strand, but again I'm really trying to limit that struct size, so I'm instead going to store a single normalized distance to the root and have the drag and stiffness parameters be parameters at the asset level instead. I'll be able to vary drag and stiffness along the trunk and branches using that normalized distance to the root, and that should do the trick well enough. Voila, that's it for the simulation structure. So next I just loop through the CSV rows to build the simulation buffer. Some variables are just passed as is, some are computed, and some are left blank for now. Next I walk up each strand chain to figure out the chain length and the maximum length to then, for each strand, compute its normalized distance to the root. Finally, I compute each strand's initial direction by looking up the strand's start and end points. I also built a simple draw function to draw each strand in a random color. And that gives me this. So next step, the simulation. Now, disclaimers. First, the simulation I built isn't physically based, but I don't care. It's a VFX for a video game after all, so I'll be happy if it looks believable enough. Second, the simulation isn't framerate independent. So let's use subticking to create a fixed tick rate. And let's tick this 240 times a second. Sounds like a lot, but these kinds of algorithms need quite a few iterations to be stable. And a high tick rate isn't likely to be an issue once ported to a compute shader on the GPU. Third and last disclaimer, the simulation has, for now, a few limitations. Some physical behaviors are not supported, but that's the price to pay for keeping things as cheap and simple as possible. More on that in a second. Alright, let's finally dive into it. How is that simulation working? Well, there are two key principles, and I'd argue the simulation can almost be seen as an emergent behavior, in a way. How so? Well, the algorithm only cares about a single strand at a time. There's no walking up or down the strand chain to propagate transforms and whatnot. And to summarize, I'm merely going to apply 2 constraints on each strand's start and end points. That's it. But remember, a strand is always connected to another strand, except the root strand. So modifying a strand's start point modifies the parent strand's end point. And that's the first property that creates an emergent behavior. That's the main thing that propagates forces and constraints across the entire structure. So let's focus on a single strand, because again, that's the only thing the algorithm does. That strand in the simulation buffer is actually just a single point, a particle, right? But I can think of it as a strand because I know its parent particle and where it is located. So that particle has a position, and at the last subtick it had a position. And again, the delta between these 2 positions divided by the tick rate gives me that particle's velocity. So first I scale that velocity down to apply drag. To that velocity I can also add extra forces. It could be wind, it could be gravity, it could be the mouse pulling on that point, like in my demo, anything really. So next I apply that velocity, meaning first the previous position becomes the current position, and the current position is updated based on the velocity times delta time. And that gives me this. Not that interesting, but kinda fun already. Next, constraints. Like I said, there are 2. First, once the velocity has been applied and that particle's position updated, that strand is now probably either compressed or stretched. However, I know this strand's initial length, it's part of the simulation data, remember? Thus I can simply ensure the distance between these 2 points always equals that initial length. So get the distance between these 2 points and compare it to the strand's initial length. The delta tells me the amount of compression or stretch to fix. So to maintain a strand's length, there are 3 different cases. First case, that strand happens to be the root strand. So I can't affect this root point. It must remain at 0, 0, 0 for the foliage instance to remain connected to the ground. Thus, the length constraint is solely applied on the strand's endpoint, meaning I just offset that particle along that direction by how much that strand is above or below its initial length. Second case, that strand is parented to another strand, the most likely scenario. Well, I still apply the same constraint but by half the amount, and the remaining half is applied on the start point, in the opposite direction. So that strand acts like a spring. And if you think about it, this constraint on that strand is going to screw up the parent strand's length, right? But then I'm going to apply the same constraint on that parent strand, and something interesting is going to happen. It's going to pull on these 2 points to maintain that strand's initial length, same as before, and thus potentially mess with this strand's length again, and its own parent strand's length, and so on and so forth. Thus changing the position of a single point has a cascading effect on the whole structure. And so at any given time it's unlikely that these strands do have the correct length, because fixing one strand screws others, if that makes sense. So it's a bit of a feedback loop, right? But the simulation is eventually going to converge towards the correct solution, and does so the faster it is ticked. That's why it needs to run at a high frame rate. The slower the tick rate, the more error and the more springy it's going to look. Third and final case, that strand is parented to a strand somewhere along its main axis. And here I assume the best way to apply that constraint is to apply half the constraint on that point still, same as before, but then distribute the remaining half between these 2 points, based on the normalized distance along the parent strand. In that case, a bit more here and a bit less there. And so that one constraint alone, applied on and on all strands, creates an interesting simulation already. It looks a bit floppy and lifeless though. So how to breathe some life into it? Well, there's a second constraint, the stiffness constraint. Remember, each point stores the strand's initial direction. So once that first spring constraint has been applied, I'm going to offset each particle in that initial direction by some arbitrary amount. Simply put, the bigger the offset, the higher the stiffness. Next, I'm going to apply a length constraint once again, but only on the endpoint to once again maintain this strand's initial length, but without the spring behavior. Here, assuming the initial strand direction is straight up, that particle, once that second constraint is applied, tries to aim towards that initial direction. And that creates a sort of angular spring effect with a baked-in fall-off. So apply that constraint on top of the first one, on and on all strands, and ta-da! Except that there's a slight issue. There's no direction inheritance, if that makes sense. See, I'm pulling on that particle, laying the root strand flat, and the rest of the structure tries to maintain its initial shape, based on each strand's initial direction, as expected. But ideally, that initial direction would inherit from the parent orientation, if that makes sense. Fortunately, that's not too hard to apply, thanks to quaternions. The idea is to fine-tune the stiffness constraint a tiny bit. First, for each strand, get its parent strand's initial and current direction. That's 2 unit vectors, so you can super easily get the smallest geodesic rotation to go from one to the other using quaternions. Next, when applying the stiffness constraint, simply multiply each strand's initial direction by that quaternion, and thus apply the parent strand's delta rotation. And now it's working. Very cool. No, this is not perfect, but how could it be? It's so simple. First limitation, there's no sense of torque or angular momentum or anything alike. See how I'm pulling on this particle? Well, I would kinda expect this to create a torque on the parent strand, right? And thus to create a rotation along that axis. And thus for this child strand to rotate a bit along that axis as well. That doesn't happen here, but again, this is a very simple simulation. You can for sure implement that. You could add more data per point and add more complexity to the algorithm, but do you need to? We are pushing foliage around in a video game after all, so is this good enough? Maybe, maybe not, up to you to decide. You may look into extended position-based dynamics and other papers to take this simulation to the next level, add support for angular momentum and whatnot. Again, up to you. I think that for a first draft, this is decent enough, especially because that's only the tip of the iceberg. Because sure, I got a cool looking simulation, but how to deform a mesh with it? So once again, this is a proof of concept, so I'm not going to focus too much on performance here, at least on the blueprint side of things. Alright, once the simulation is done, each frame, I'm going to loop through the simulation buffer and compile the data to send to the shader. But first, let's brainstorm a bit. Have a mesh and a strand hierarchy somewhat closely matching this mesh. How can it be deformed according to this strand simulation? Well, you probably guessed it, I'm going to use a Vertex Shader to simply offset vertices. Emphasis on offset. What do I mean? Well, let's assume I'm 10 steps ahead, and I already figured out how to deform the mesh with the simulation data. This strand simulation, at rest, should result in no mesh deformation at all, because the mesh rest pose already matches the simulation's rest pose, okay? Which means I only care about how much each strand quote-unquote has moved relative to the rest pose, an offset, if that makes sense. Same idea for the rotation, I only care about how much each strand is rotated relative to the rest pose. Moreover, a rotation is computed around a pivot point, so it looks like I kinda need to keep track of each particle's initial position after all. Hence the extra array here. Now I could make that vector be part of the simulation struct, but whatever. To summarize, I need to send the shader 3 things: an offset, a rotation, and a pivot point for that rotation. So first, the offset is simply the delta between the strand start point's current location and initial location. The pivot point is just the strand start point's initial location. And finally, for the delta rotation, the smallest geodesic rotation to go from the strand's initial direction to its current direction will do just fine. Neat. How would I go about sending that data to a shader though? Well, a render target would do the trick. Store each piece of data in a pixel and that's it. Let's think about it though. I would have an XYZ offset in RGB, an XYZ pivot position in RGB as well, and a quaternion in RGBA. That would be 3 render targets in total. That's a lot. That'd be 3 texture samples per vertex, and that's way too much to my liking. Texture samples are expensive, they induce lots of latency due to memory fetches, so let's try to be smart and use bit packing to optimize this. First, a quaternion can be packed into a single float with decent precision. The smallest 3 components method is the most popular technique to do so. And Niagara has built-in functions to handle that, as well as the material graph. Neat. So I could store the offset in a 32 bits render targets RGB channels, and pack the quaternion in the alpha channel. I'd still need a second render target for the pivot XYZ position though, not ideal. Well, actually, no, not necessarily. You see that offset and pivot point are both in local space, relative to the instance origin. So it's unlikely I need 32 bits of precision. 16 bits should be enough, even for large trees. So let's convert the offset and pivot position X, Y and Z components to 16 bits and pack them together in the 32 bits red, green and blue channels to use one and only one render target. But how so? Well, Niagara to the rescue. I feel like it has become the go-to method to write data into render targets. So normally I would create 3 user parameter arrays that I would set in blueprints, but let's try something new. Let's try using a Niagara data channel for once. So I created one, a global channel to contain 2 vectors and a quaternion. Then, before looping through the simulation data, I'm preparing the data channel for that amount of writes. During the loop, I can then simply write 2 vectors for the offset and pivot position and write a quaternion for the delta rotation. In Niagara, I can then use a simulation stage to iterate over the render target pixels. And for each pixel linear index, I can attempt to get the data stored in that data channel at that index and write it into the render target. The offset and pivot point are converted to 16 bits and packed into 32 bits float, and the quaternion is packed into a single 32 bits float. Cool. Before doing that though, I simply copy that render target into a second render target. That's to make the simulation double buffered and have access to the simulation data from the previous frame. That's to be able to create a material that can write to the velocity buffer, quite important. And that's it, the simulation is now quote-unquote exported and written into a render target that can then be sampled in any material. So the quaternion bit packed into the alpha channel can be simply unpacked using this built-in material function. Great. And the 16 bits offset and pivot point need to be manually unpacked using HLSL the same way they were packed in Niagara. Okay, so to apply the strand rotation, I'm going to take the position delta between the vertex position and the pivot point, both are in local space, to apply a local rotation with that quaternion. The resulting rotated vector then needs to be converted into an offset. And finally, I can simply add the strand's offset. Duplicate that for the previous frame position, use the previous frame render target, and then rotate the vertex normal in local space by that quaternion again to compute a new tangent space normal. That's it, it's actually quite cheap. But there's one remaining challenge. Each vertex needs to know which strand it is quote-unquote parented to, and thus which pixel to sample in that render target. And at this point, the method is really similar to the skinning method used for skeletal animation textures. You could use a weight texture to parent a vertex to multiple strands, but I'll keep it simple here. I'm simply going to use a second UV map to encode a single parent strand information. See 0, 1, 2, 3, 4, and so on. That UV map horizontal axis stores an integer for each vertex that points to the strand index that vertex is parented to, if that makes sense. Now that's easily done with such a simple and disconnected mesh, but it's a bit less straightforward with a more organic mesh. So I wrote a tiny Blender script to loop through all vertices, figure out each vertex highest weighted group, and update the UV map accordingly. It's a bit sketchy for reasons I'll skip for today's video, but that's the gist of it. It's nothing too complex after all. See, that's the root strand, index 0, first strand, index 1, and so on and so forth. Keep in mind, UVs are stored in a pair of 16 bits float by default in UE, and the amount of integers that can be accurately represented by a 16-bit float is limited. If this is an issue, there are techniques to store integers in floats using bit packing, similar to what Pivot Painter does, and other methods as well. In UE, I can then use that second UV map to tell each vertex which pixel to sample in that render target along the horizontal axis. Now, there are two important things. UVs must be offset by half a pixel to be centered on each pixel, because the render targets must use unfiltered pixels to enable nearest pixel sampling and prevent linear interpolation. That would screw up the bit-packed quaternion and the two 16-bit packed vectors as well. So that's critical to enable this. And voila, that's it. Quite a journey, right? And that's only the beginning. Next, I'll have to port the blueprint simulation to compute shaders, but that shouldn't be too bad thanks to Niagara. However, that means the strand hierarchy will also need to be built in compute shaders. I'll likely pre-compute that data into a separate render target to also support multiple foliage types though. Meaning for each foliage instance to simulate, I'll just be able to point to a pixel in that render target to inject the necessary strand hierarchy into the simulation buffer. Next, I'll have to support multiple instances because for now, working with one single instance was easy. That render target, for instance, is just one row of pixels with one single hierarchy, so it's easy to work with. But a second instance would need to know where its own data is located at, and it could be spread on 2 rows, so I'll have to handle UVs a bit differently. And many other things, but that will be for another day. That's enough for now. I hope you liked the video. Feel free to like and subscribe to the channel if you did. Files are available as a tier 2 reward on my Patreon, as well as many other educational projects, demos and assets. Thanks for watching, and thanks to all my patrons for the incredible support. Stay tuned for the next video, take care of yourself, bye bye!